Okay, so today we're going to continue talking about equivalence classes. Okay, so let me just remind you what an equivalence class is, because we defined it at the very end of last time. We said that if you have an equivalence relation, which is a relation that's reflexive, symmetric, and transitive, then one thing you can do is, well, for example, let's take congruence modulo 3, which is an equivalence relation. We can look at all of the elements that are congruent to 0 modulo 3. Right, so 0 is congruent to 3, and it's congruent to 6, and it's congruent to 9. But since it's an equivalence relation, it's transitive. Right? So if 0 is congruent to 3 and 0 is congruent to 6, it means that 3 is congruent to 6. So basically, everything in this top blue circle is equivalent to everything else in that circle under the equivalence relation. And so what we can do is we can take all of these elements together as one big set. So that contains infinitely many integers. It contains all the multiples of 3. And we could just call that, but we could throw them all into a single set. And this set we could denote like this. This means the set of all objects, the set of all the integers that are equivalent to 0 under this equivalence relation. And one thing we noticed in this case is, well, every single integer is in one and only one of these equivalence classes. And today we'll see that that's true in general. Okay, so that this was what we made the definition. Take any equivalence class on a set A, then for every element in A, you can talk about the equivalence class of A. It's a big subset of A, consisting of all things that are equivalent to this little a. Okay, and we saw one example. We had the same state equivalence relation, and essentially here the equivalence classes basically correspond to the states, right? So Seattle, the equivalence class of Seattle is all the cities in Washington. The equivalence class of Tacoma is all the cities in Washington. So these two are the same equivalence class. They just have different names right now, right? But these denote the same sets. So these two sets are actually equal, even though Seattle and Tacoma are not equal. So let's think of some more examples of thinking of these equivalence classes, right? So really, we only, I think, saw 3 equivalence relations last time. We saw a bunch of relations, but only one of them, 3 that were equivalence relations. One of them was R equals the equivalence relation on R, given by equality. Right, so again, generally in this equivalence class, with this equivalence relation, instead of writing R equals B, we say A equals B. This is normally how we denote this equivalence relation. So what are the equivalence classes? Well, like if I take a look at the equivalence class of pi, say, what is this? This is the set of all elements of the reals such that x is equivalent to pi, but the equivalence relation here is equality, so that such that x is equal to pi. What is this set? This set is just the singleton set pi. Pi is the only real number that's equal to pi. So for this equivalence relation, there's an equivalence class for every single real number. A different equivalence class, say A, for every real number A. Right? Every equivalence class is just a single element, and so there's an equivalence class for every single real number A. Did we have any other equivalence relations? I said 3, but so no, we actually only had just the 2 equivalence relations, but congruence modulo n, I see. We already talked about congruence modulo n, but let's talk about another example of congruence modulo n, which is, let's consider congruence modulo 2. Right, this is an equivalence relation on Z. What are the equivalence classes? Well, let's write some down. The equivalence class of 0, that's the set of all integers Z such that x is congruent to 0 modulo 2. So what are these things? this is a set of all x and z such that there exists an integer k such that x equals 2k, because that's the definition of being congruent to 0 modulo 2. Or if we were to write out all the elements, what do we have? 0, 2, 4, 6, 8, -2, -4. This equivalence class is often called the even integers. So you can think of the even integers as the equivalence class of 0 modulo 2. That's another way to talk about the even integers. By the way, again, an equivalence class can have more than one name. This is also the same thing as the equivalence class of 10. Right? So these two things, again, are equal. These are actually the same thing. They can just, it just has more than one name. Right? And then the equivalence class of 1, this is a set of all x and z such that x is congruent to 1 mod 2. This is called the odd integers. Okay, so anytime you talked about the evens or the odds, which you did even in elementary school, what you're doing is we were talking about a certain equivalence class under the equivalence relation given by congruence modulo 2. Okay, so again, in all of these examples, actually, if you look at all possible equivalence classes, in this example, there's only two possible equivalence classes. There's the evens and there's the odds. Every single integer is in one of these two equivalence classes and only one. With the equality on the reals, there were infinitely many equivalence classes. There's one for each real number. But again, every real number was in one and only one equivalence class. It turns out that this is true in general, which we'll prove, but here's a fact. Given if this is an equivalence relation on A, then the equivalence classes partition A. I will, in a second, define the word partition. Let me first prove the theorem, and then I'll define partition, right? Basically, partition just means that you cut up A into different pieces that cover all of A but don't overlap. Okay, so here's the theorem. Here's the precise way to say this. So let A be a non-empty set. And let this tilde be an equivalence relation on A. On A. Then three things are true. One, for every A in A, you can find A in an equivalence class. Which equivalence class can you find A in? You can find A in the equivalence class of A. Okay, 2, for all A, B, and A is equivalent to B if and only if the equivalence class of A is equal to the equivalence class of B. And 3, for all A, B, and A, if you look at the equivalence class of A and the equivalence class of B, either these are equal or they intersect in the empty set. They're disjoint. Okay, so what does this really say? Part 1 says that every element is in at least one equivalence class. So if I look at the set of all possible equivalence classes, every element in A is in at least one of them. Namely, it's in the one that is the equivalence class of itself. Okay, part 2 here says sort of two different things. One thing that it says is that if you take two equivalent elements, again, these could be different equivalent elements, right? I'm not saying they're equal, but they could be different equivalent elements, then they will determine the same equivalence class. The equivalence class of A will be exactly the same as the equivalence class of B. But because it's an if and only if, it also says that if A and B are not equivalent, then they determine different equivalence classes. So if you take two non-equivalent elements, you'll get two different equivalence classes. But part 3 says something even stronger, which is if you take any two elements, either they have the exact same equivalence class, or if they have different equivalence classes, not only are they different, they're actually disjoint. So they don't overlap at all. So if you put all these three things together, what it says is that every element is in an equivalence class, and every element is only in one equivalence class, right? Because if you look at every other equivalence class, either it's the same equivalence class or it doesn't intersect at all, so they don't share any elements. This means that every element of A is in one and only one equivalence class. I can even tell you which one it is. It's the equivalence class of A. That's really what this theorem is saying. Every A in A is in one and only one equivalence class, namely A. Okay, now A, the equivalence class of A there might be other ways to refer to it, right? So again, with these evens and odds, every integer is in one and only one equivalence class, right? 35 is in one and only one equivalence class. It's in 35. It's not in any of the others, but this is also called the equivalence class of 1. Okay, so let's prove this theorem. Actually, the proof of this theorem is not so hard. Okay, so 1, I need to show something is true for all A and A. So let's let A be an A. I need to show that A is in the equivalence class of A. What does that mean I need to show? It means I need to show that A is in this set. Let me put this in blue because it's not in the statement of the theorem. I need to show that A is in the set of elements that are equivalent to A. Why is that true? That's true because it's an equivalence relation, so it's reflexive. Since tilde is reflexive, A is equivalent to A, hence A is in A. This is by definition the set of all elements which are equivalent to A, and A is equivalent to A. So that shows that every element is in at least one equivalence class. 2, we need to show an if and only if. So let's do this direction first. So suppose that A, B are elements of A with A equivalent to B. We wish to show that the equivalence class of A is equal to the equivalence class of B. How do we show this? We can show both inclusions, right? So let me nest one level deep. So suppose X is in the equivalence class of A. What does that mean? That means that X is equivalent to A. But now, look, X is equivalent to A and A is equivalent to B, and equivalence relations are transitive. So since this is transitive and X is equivalent to A and A is equivalent to B, this will imply that X is equivalent to B. Hence, X is in the equivalence class of B. Right, and then to show the reverse inclusion, just do the same thing, but reverse the roles of A and B. You actually also might need to use symmetry, I guess, to flip around one of the equivalences, but I'll leave that as an exercise. So that shows that if A is equivalent to B, then the equivalence class of A is equal to the equivalence class of B. What's the reverse direction of this? Now suppose that the equivalence class of A is equal to the equivalence class of B. Well, by part 1, A is in the equivalence class of A, but the equivalence class of A is equal to the equivalence class of B. But since A is in the equivalence class of B, that means that A is equivalent to B by the definition of the equivalence class of B. Okay, so this shows that if you have two elements, if they're equivalent, then they have the same exact equivalence class. If they have the same exact equivalence class, then they're equivalent. Right? So this says that equivalent elements determine the same equivalence class, non-equivalent elements determine different equivalence classes. What we don't know yet, though, is that all those different equivalence classes are actually disjoint, right? At the moment, from what we've proved so far, maybe if you can have two different non-equivalent elements, they determine different equivalence classes, but there's some overlap between them, even though the equivalence classes are different, right? So, but part 3 of this theorem rules it out. So proof continued, part 3. So let A and B be elements in A. We want to show that either they determine the same equivalence class or the equivalence classes they determine are disjoint. Okay, now there are two cases. Either these equivalence classes are disjoint or these equivalence classes are not disjoint. Again, anytime you do casework, you should make it very clear to your reader that the two cases cover every situation. Okay, now in the first case, we're done. Right? I need to show that either this happens or this happens. In the first case, the second thing just happens. So I might as well assume that we're in case 2. Right, so suppose now that the equivalence class of A is intersect the equivalence class of B is not the empty set. I need to show that in this case, the equivalence class of A is equal to the equivalence class of B. Well, then there exists some element C in A such that C is in the intersection. That's what it means to say that the intersection is not the empty set. So C is in A and C is in the equivalence class of B. Therefore, since C is in the equivalence class of A, C is equivalent to A, and C is equivalent to B. This is by the definition of the equivalence class of A and the equivalence class of B. Now what do I need to show? I need to show these two equivalence classes are equal. Right now I know that they share an element. But by part 2, if I knew that A and B were equivalent, then I would know that they determine the same equivalence class. Well, I know that C is equivalent to A and C is equivalent to B. Now I know by symmetry, A is equivalent to C. So by transitivity, A is equivalent to B. So by part 2, the equivalence class of A is equal to the equivalence class of B, which is what I wanted to show. I wanted to show that if the intersection was not empty, then actually the two equivalence classes were equal. Okay? So what we've shown is that every element of A is in one and only one equivalence class of this equivalence relation tilde. Right, so what this means is that we can take this whole set A, and if I look at every single element in A, it's in some equivalence class. Right, so if this is like little a, then this green thing is the equivalence class of A. And it could contain some elements, right? Some other elements. But the point is now, if you look at every single element in A, it's in one of these equivalence classes, and it's in only one of these equivalence classes. These equivalence classes don't overlap at all. So what you can do is you can cut up A into these different pieces, and every single element of A will live in one and only one of these equivalence classes. So we can divide A up into a bunch of disjoint equivalence classes that covers all of A. That's what we can do because of this theorem. And this is what we call a partition. So let me just define that. So let's let A be a non-empty set. And let's let C, script C, be a collection of subsets of A. Okay, so I have a big set A, and I've got a bunch of different subsets of A. We say that C is a partition of A if the following three things hold. One, for every set in this collection, it's non-empty. So C must consist of non-empty sets. Two, for every x in A, there exists some set in C such that x is in V. So every element of A is in at least one of the subsets in C. And three, for every V and W in C, either V equals W or V intersect W equals the empty set. This says that if you look at all of these sets inside of your collection of subsets, they don't overlap. Another way to say this is that the elements of C are pairwise disjoint. Every pair of them is disjoint, intersects in the empty set. Right, the distinct elements of C are pairwise disjoint. Okay. So really, what does this say? This first one just throws out some useless subsets of C. So C is going to be like a way to cut up A, right? C is going to be a bunch of pieces of A, but we're not ever going to include the empty set as any of these pieces because we might as well throw them away. So one is like a non-triviality condition. It's just a technical condition. I'll never include the empty set in a partition because again, if I'm going to cut up A into pieces, why would I include any empty pieces? Two says that every element in A is in at least one of the pieces in C. And then three says that the pieces in C don't overlap. This means that you can cut up A into a bunch of non-overlapping pieces. That's what a partition is. And this previous theorem says exactly that if you have an equivalence relation, the equivalence classes partition A. Okay, so we already have some examples. One, if I take A to be the set of integers, and I'll let C be the following collection of subsets, I'll take the even integers, comma, the odd integers. Then C is a partition of A because C consists of a bunch of subsets of A, right? The even integers, that's a subset of A. The odd integers, that's a subset of A. Every element is either even or odd. We proved that very early in the class. And every element is even or odd, but not both. That means precisely that these two equivalence classes cover that these two subsets cover every integer, but are disjoint. Every element is in exactly one. So that's a nice example of partition. We can also be a bit more artificial. I could take A to be the set A, B, C, and C to be a set of subsets. I could take, say, the subset A by itself and the subset consisting of B, comma, C. There's a partition of A. All I've done is I've cut up A into two pieces, and I've thrown those two pieces into my collection C. Okay, 3. I could let A be the real numbers. And I could let C be the set of all half-open intervals where X is an integer. This is a nice partition, right? It's like I'm taking the number line and I'm cutting it up into half-open intervals of length 1 that shift by 1 as you go down. So this is just cutting up my real line into pieces of length 1. I have to be careful at the half-open interval to make sure that the sets don't overlap. Okay, and then my last example, you can take A equals 0 to 1. I can choose a natural number, n, and I can let C be the following collection of half-open intervals: 0 to 1 over n, 1 over n to 2 over n, 2 over n to 3 over n, dot, 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 up to n minus 1 over n to 1. And I'll make this one closed just to make sure I cover everything. Right? What am I doing here? It's like I'm taking the interval from 0 to 1, and I'm just chopping it into n equally sized pieces. And the reason I bring up this example is because when you define the definite integral, you take it as a limit of Riemann sums over these kinds of partitions. You partition the interval, right? You take like a sample point inside of each element of the partition, and then you find the area of the rectangle, and you call it the Riemann sum. And then you take the limit as n goes to infinity, and that gives you the definite integral. So even in calculus, you were dealing with partitions when you were taking Riemann sums and defining definite integrals. Okay, so a partition is a very general kind of phenomenon. There are lots of times you want to partition. It's just to cut up a set into a bunch of disjoint pieces. And let me just state this theorem. It's really a corollary. So let tilde be an equivalence relation on A. Then if I take C to be the set of all equivalence classes of tilde, then C is a partition of A. Okay, really, this is just a restatement of the theorem that we just proved on equivalence classes. This theorem, again, precisely says, if you read through the definition, that if you take all the equivalence classes, these partition A. So all I've done is I've just stated it in the language of partitions. Okay, in particular, here's another corollary. I can apply this specifically to congruence modulo n, right? So congruence modulo n is an equivalence relation on Z. So let's let n be a non-zero integer, sorry, a non-zero natural number. Then for each integer A, let's let A be the congruence class, or the equivalence class of A modulo n. Then we know that these equivalence classes, all the different equivalence classes, partition Z because of the previous corollary. That means that 1, Z you can write as the union of these equivalence classes. Okay, again, here, the tricky thing here is that this thing is like a whole set of integers, right? This thing is like a whole set of integers. So I can take their union and get every possible integer. Then 2, if you take two integers inside of this range, then if they're not the same one, then these equivalence classes are disjoint. Okay, now why, all I'm doing is I'm just restating results just in terms of congruence modulo n. But the point is that actually congruence modulo n is one of the most important examples of equivalence relations. And its equivalence classes are one of the most important examples of equivalence classes. Okay, so one thing that we showed previously in the quarter is that you can do arithmetic with congruence modulo n. So let me just start a new slide here because I want to have all these stuff on the same slide. So we showed long ago that you can do arithmetic with congruence modulo n. So we said, for example, that 2 plus 4 is congruent to 6, which is congruent to 1 modulo 5. Right, we said stuff like, oh, well, since 2 is congruent to 7 modulo 5, then 2 plus 3 is congruent to 7 plus 3 modulo 5. Okay, so here we were taking, potentially different integers. 2 and 7 are different. But from the perspective of congruence modulo 5, they're the same. And so you can do arithmetic, you can add, you can multiply, and it all makes sense modulo 5. So this kind of arithmetic, here I'm using integers and congruence modulo 5. Here, these are actual integers. To say that 2 plus 3 is congruent to 7 plus 3 mod 5, I really mean that the integer 5 and the integer 10 are congruent. Okay, but we can also do arithmetic with congruence classes modulo 5. What do I mean? I mean that we can write things like the equivalence class of 2 plus the equivalence class of 4 equals the equivalence class of 6 equals the equivalence class of 1. Or I should be able to say something like, well, the equivalence class of 2 is equal to the equivalence class of 7. So the equivalence class of 2 plus the equivalence class of 3 is equal to the equivalence class of 7 plus the equivalence class of 3. Now, what I'm saying is it seems like we should be able to do this. Now, certainly this equality is fine because the equivalence class of 6 is the same thing as the equivalence class of 1. What's bad here is I just wrote this down, but technically what I've written down doesn't make any sense because I haven't defined an operation on these two sets. Right? This is the set consisting of all integers which are congruent to 2. This is the set of all the integers that are congruent to 4. What do I mean when I say when I add them? Well, the point is that if you take any element from this equivalence class and any element from this equivalence class, you will always get something that's in the equivalence class of 1. However, I don't have any definition of how to add sets like this. So when I mean, oh, take anything from this set and add it to anything from this set, I'll use a different symbol. I'll use a symbol which is the plus sign with this circle around it. That's what your book uses. Okay, so what this means, is just take any element from this equivalence class and add it to any element of this equivalence class, and you'll get an element inside of this equivalence class. By the way, in LaTeX, the way to get this is \O+, because there's a plus with an O around it. So it turns out that you can actually make sense of statements like this. Adding the equivalence class of 2 to the equivalence class of 3 is the same thing as adding the equivalence of 7 to the equivalence class of 3. The point I'm trying to make here is you can do arithmetic using equivalence classes instead of integers, and equality of sets. So there's two different ways to think about congruence modulo 5 and the arithmetic you can do. You can either use actual integers and actual addition at the expense of taking congruence instead of equality, or you can take the set of equivalence classes. There are only 5 equivalence classes. There are infinitely many integers. There's only 5 equivalence classes. And you can define an operation of addition on the equivalence classes. And you can do arithmetic with the equivalence classes. But now you actually get equality. The equivalence class of 6 is actually equal to the equivalence class of 1. Whereas 6 and 1 are not equal. They're just congruent modulo 5. And to be honest, the way that most mathematicians think about congruence modulo 5 is actually this bottom way. We think of 2 and 12 as the same because we're really thinking of the equivalence class of 2 and the equivalence class of 12. And so those are the same. We've just changed our operation to be this new operation, O plus, between equivalence classes. Okay, so let me introduce a new piece of notation, essentially, a new definition. So let n be a non-zero natural number. Then the set of congruence classes or equivalence classes for the relation, the equivalence relation, congruence modulo n, is called the set of integers modulo n. If I look at the set of congruence classes, the set of equivalence classes, I call that the set of integers modulo n. And we denote this set by z subscript n. Okay, what do I mean by this? Let's give an example. Okay, so if I look at z sub 5, z sub 5 is the set of congruence classes for the relation congruence modulo 5. There are exactly 5 of them. Z sub 5 consists of the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, the equivalence class of 3, the equivalence class of 4. That's Z5. It only consists of 5 things. The equivalence classes, the elements of Z5 are entire sets of integers. But I can think of this very compactly because when you do arithmetic modulo 5, right, basically these are the only 5 elements that really matter. So the integer 7 is congruent to the integer 2. So if you're doing anything with 7, you might as well do it with 2. The abstract way to think about this is that 2 and 7 live in the same equivalence class. So I'll just think about equivalence classes rather than thinking about integers. Okay, Z2 is 2 equivalence classes. And again, this is like the evens and this is like the odds. So way back in elementary school, when you learn stuff like, oh, an even plus an odd is an odd. An even plus an odd is an odd. It's like you're doing arithmetic with an entire equivalence class of integers. An even plus an odd is an odd is just the statement 0 plus 1 equals 1. The equivalence class of 0 plus the equivalence class of 1 is equal to the equivalence class of 1 under this operation O plus. Okay. I haven't really defined this yet, by the way. I've just tried to do it by example. So let me discuss a little bit more about this notion of arithmetic with equivalence classes. And again, this is the way that people actually think about congruence modulo n most of the time. Okay, so one thing we proved earlier is that if A is congruent to B mod n and C is congruent to D mod n, then A plus C is congruent to B plus D mod n. This is a thing that we proved a long time ago. And what did it really say? It said that, well, if you're going to add two numbers together, if you're going to add A and C, you could replace, and you only care about the result mod n, you could replace A and C with anything that they're congruent to modulo n, and it doesn't change your answer. You can take any element in the equivalence class of A, and you can add it to any element in the equivalence class of C, and you always get an element in the equivalence class of A plus C. That's another way to state this result. Take anything in the equivalence class of A and anything in the equivalence class of C, and if you add them together, you always get something in the equivalence class of A plus C. So I can translate this to the following. If A and B have the same equivalence class, so this is in new language. If A and B have the same equivalence class, and C and D have the same equivalence class, then A plus C and B plus D have the same equivalence class. So since I want to think about Z5 as opposed to congruence modulo 5, let me state this as a theorem that we can use and we can cite. So let n be a non-zero natural number. Let A, B, C, D be integers. Then inside of Z sub n, 1, if A equals B and C equals D, then the equivalence class of A plus C equals the equivalence class of B plus D. 2, if the equivalence class of A equals the equivalence class of B, and the equivalence class of C equals the equivalence class of D, then the equivalence class of A times C equals the equivalence class of B times D. This is if you want to multiply. If you take anything in the equivalence class of A and anything in the equivalence class of C, and you multiply them together, you always get something that's in the equivalence class of A times C. 3, if A is equivalent to B and M is a natural number, then the equivalence class of A to the M is equal to the equivalence class of B to the M. So this is just a rephrasing of that previous theorem. So this is not new information. And in fact, there's not even any new operations here. All I've done is I've just rephrased, instead of saying these things are congruent modulo n, all I'm saying is, oh, they have the same congruence class. That's the same thing though. But notice here that I'm not actually adding equivalence classes in this theorem. Here, I'm not adding equivalence classes. All I'm doing is I'm adding integers. I'm adding A plus C as integers and then looking at their equivalence classes. All the equalities here, these are not congruence modulo n. These are just equalities of sets. Right? This is equality of sets. However, what this theorem basically will say eventually is that it makes sense to add two different equivalence classes. Because if you take the equivalence class of 2 and the equivalence class of 7, those are the same equivalence class. If I add them to the equivalence class of 3, I get the equivalence class of 0. So I want to define an addition on equivalence classes, which I've already alluded to with this O plus. Let's just define it here. Here's the definition. Let n be a non-zero natural number. Then we can define an addition and multiplication inside of this set Zn. Again, Zn is a set of equivalence classes. So I'm going to define what it means to add and multiply two equivalence classes. So if I take any two equivalence classes inside of Zn, I'll define the addition of A and B and the multiplication of A and B. Again, here I need to use new symbols because I don't want to confuse myself with the addition of integers because A and B are two big sets. So I'm going to define addition of two equivalence classes, and I'm going to define multiplication of two equivalence classes. Okay, so I already said this, but this is O plus. This one is O dot, I believe. How am I going to define it? I'm going to define this to be a new equivalence class. It will be the equivalence class of A plus B. And this one I'll define to be the equivalence class of A times B. Okay, so this one is the new operation. I'm defining the sum of two equivalence classes. This one is the old operation of addition of integers. Okay, so here I've defined an addition, a new addition, and new multiplication on the set Zn. So let's go back to our example. If I take a look at the set Z sub 5, again, this consists of just 5 equivalence classes. There are many names for these equivalence classes, but there's only 5 of them. And what I've done is just defined an addition on these equivalence classes. So for example, I defined the sum of the equivalence class of 1 and the equivalence class of 3 to be the equivalence class of 1 plus 3, which we know how to do. That's the equivalence class of 4. I've defined the equivalence class of 3 plus the equivalence class of 3 to be the equivalence class of 3 plus 3, which is the equivalence class of 6. But we know that that's the same thing as the equivalence class of 1. Okay, so the point I'm trying to make here is the difference between this newly defined operation and this old operation. Similarly, if we take the equivalence class of 4 times the equivalence class of 2, I define this to be 4 times the equivalence class of 4 times 2, which is the equivalence class of 3. And the whole point is that this theorem guarantees that this definition makes sense. We need this theorem in order to make sure that this definition makes sense, because if I didn't know that theorem, then if I took a different name for this equivalence class, if I took, oh, well, I could call this equivalence class of 6, and if I add it to the equivalence class of 3, it seems like I could get a different answer. So it wouldn't be a well-defined addition, but it turns out that you do get the same answer because these two are the same equivalence class because of this theorem. Okay, so when mathematicians think about doing arithmetic modulo 5, most of the time, we just think of these 5 elements. These 5 elements are entire equivalence classes of integers. And we think about these two operations. We think about these two operations on this set of equivalence classes. So it's like I'm thinking about multiplying an entire equivalence class by another entire equivalence class, but it all makes sense because you can do arithmetic with equivalence classes modulo n. Okay, so you will, again, return to this set when you take whatever the algebra sequence is, Math 402. And there's also the one for teachers, which is like maybe 412. Don't quote me on that. This will be a nice example of a commutative ring, and you will use something like this notation, if not exactly this notation. Okay, so this concludes chapter 7. I'm not sure. I need to figure out the schedule for the rest of the class. We will either move on to chapter 8.1, or if I don't think there's enough time, we'll move on directly to chapter 9 in the next lecture.